like it means nothing.
Well, let's get going. My name is Antti Rössi. I work for the Finnish government, National Cybersecurity Center to be precise. I mainly work with DFIR, threat hunting, tooling and capability development there. My previous background is in private sector, DFIR and IT startups. So in IT startups, obviously CTO role does pretty much everything. So they, even today at NCSC, I like to title myself as the cyber janitor who does whatever dirty work needs to be done to get some certain impact. I wanted to tell you one brief slide about NCSC because before I joined the agency roughly 2 years ago, I had absolutely no clue what does the NCSC do, like in Finland, but also in general, what is the role of an NCSC usually within the government. So the Finnish NCSC is part of Traficom, the agency of transport and communications. In different EU countries, the NCSCs live in other parts of the governmental organizational structure, but this is where we are in Finland. And we have a lot of different tasks and obligations that we're working with, but I'm going to tell you a couple of things from the new EU cyber legislation, the EU Cyber Security Directive. What does it sort of oblige us as the NCSC to do? And it includes, like you can see up there, monitoring cyber threats, early warnings, vulnerability disclosure. But one of the topics most close to my heart is this responding to incidents and assisting critical entities within the society. So if you think about this, a lot of the technical work that we do at NCSC is a lot. It's pretty much the same what you do on the private sector, but the scope differences are mainly such that if you work in-house for a corporation, you defend that company. If you work for a managed service provider, then your audience and your customers are obviously the customers of that MSP. Then if you work for the government, like our main target audience and our customer is the society, so critical infrastructure, governmental agencies, other entities that are crucial for the operation of our society, basically. So the technical things are all the same, but the sort of scale where we operate just a little bit bigger than in an MSP usually. And these CCERT functions, what we call them in the directive, are just a very small part of what the NCSC does. So maybe 20, not even 30% of NCSC is what I'm talking about here today. So there are a lot of different things that we work on. But just to give you a small idea. Let's look at some ICS-related terminology before we get into the technicalities. When we talk about operational technology, that usually, if you compare OT to IT, what do we mean? How is OT different from IT? In IT, we're dealing with information, usually in some form of a virtual format, whereas in OT, we are talking about things actually happening in real life. So there's this so-called cyber-physical domain involved. Things are happening also outside of the computer. Then within OT, we have a subset of OT called ICS, which stands for Industrial Control Systems. They're essentially OT systems that are used to control industrial processes. Like if you have an automated coffee machine at home, it's an OT system, but it's not an ICS thing really, because it just makes coffee for you. But if you have a coffee factory, that's an industrial control system working with coffee. In OT, we also have, of course, there's IoT and various other things, but and within ICS, we have a lot of different weird terms that we're going to dive into very shortly. But I want to talk to you about SCADA first a little bit, because these three terms, OT, ICS, and SCADA, or as we say, SCADA in Finnish, are sometimes used synonymously, and it might be okay depending on the context, but they're definitely not the same thing. So even though SCADA systems are OT systems, but they're not the same thing as per se. Good. Let's get to the crazy drawings. We're going to have a lot of these today. So Before we go into looking at the industrial control systems, let's talk about a concept called Purdue model briefly. Now, the Purdue model is a concept that allows us to conceptualize how far away are these components that we're talking about, how far away are they from what we call the process. The process being the actual operational thing. Let's say if it's a coffee factory, you might have a process for roasting the coffee or grinding the coffee or packaging the coffee, for instance. So on the level 0, we have these so-called field devices, which are motors, valves, actuators, components that are directly influencing and touching the process, so to say. And then when we start to go up in levels, level 1 we have controls, usually it's programmable logic controllers, a little bit more about them in a second. But as we go further up in the layers, we go further away from the process, and also these devices and systems, they turn more IT-like, because the motors and valves are not very familiar to us, let's say as forensic investigators, for example. But the only thing you need to remember from this is level 0 is process, and level 2, 3, 4, 5 is very IT-like systems. Well, what does an industrial control system look like then? If we're going to talk about investigating such a environment today, let's have a look at a few examples what they usually look like. This drawing is from Trend Micro, great drawing, and I chose this particular diagram to illustrate the point that within ICS systems, you can see we can have 2 or more network segments. There's a distinct segment called the production network, where we have the field devices. In this case, there's some kind of an oil pumping thing, I guess. We see temperature monitors, some alarm bells, and whatnot. There's also an engineering workstation in there within that production network. But then next to the production network, we have the SCADA system. And if you have some kind of even semi-reasonable network segmentation going on in your facility, which you hopefully would and your customers would, then these two should be 2 completely distinct separate networks from one another. So when you're going into an incident and you hear that it's about an ICS facility, I've noticed that it makes a big difference if the attacker only breached the SCADA side of the systems or if they actually got into the production network. So it's definitely not the same thing. And then of course we have some enterprise components there. There's also usually an office on the side of an ICS facility, so obviously it's not just heavy machinery. People also need to use PowerPoint, they need to write the emails and stuff, so there's also an enterprise part of the network that is usually somehow, one way or another, connected at least to the SCADA side of the system. Now here's another example. This is a Honeywell Experion LX system diagram, and I want to show you this particular diagram and talk about a concept called reference architectures. So this is, you could say, a reference architecture of sorts. And what I mean by reference architecture is that a lot of these vendors, obviously they write public marketing materials about their products, but they also publish and even kind of compete with other vendors about how their systems are, how flexible they are, what kind of components are involved. And what I usually do first, if I'm called in to assist in an ICS-related incident, I try to figure out what vendors are present in that site. So what software is there, what hardware is there, what product families are being used there. And before ever going to the site or starting with the investigation, I like to check those product families out first and understand what kind of components do they usually contain. Now, more often than not, the actual facilities are not following the best practices and these reference architectures. And I mean, I have no idea what the PhD or profit suite is, even still up until today, but they give you a rough idea what kind of systems are you likely going to run into when you go into an environment where there's a Honeywell Experion system, for instance. Let's talk about PLCs a little bit next. Okay, so we have some overall ideas now. What about the individual components then? So here is a programmable logic controller, a so-called PLC. And this particular PLC, what makes it modular is the fact that besides having a power supply and a CPU, it also has a variable number of I/O modules, so input-output modules on the side of it. And then there's also a comms module, but These are the devices where the automation logic of that facility lives in. So the automation engineers, they write code for PLCs. And PLCs, the I/O modules of these PLCs are directly hooked onto those motors and valves, the level 0 components that I talked to you a few slides ago about. So these are like the brain or the heart of the facility. And now, thankfully, in a lot of investigations that consider ICS facilities, you don't necessarily need to or have to go to investigate PLCs. If you do, it's not a very nice thing to do. But even if you don't touch them, you need to understand what they are and how they work, so that you can assess: do we actually need to go and have a look at the logic of the system? Has that maybe been altered? Then another super important component besides the PLC is what we call an HMI. This was mentioned in the Purdue model picture as well on the level 2. So HMI stands for human-machine interface. And no matter how crazy this looks to us, coming from maybe cybersecurity or IT backgrounds, this is the reality for these so-called traditional engineering craftsmen who work with these facilities and systems. And this is the way how they monitor the operations of an industrial process. But not only monitor, what's funny to me, I didn't realize this when I saw some of the first HMIs ever, that these are actually also used to control the process. So if you have a look at those what do you call those pump-like symbols there, some of them are red, some of them are green. In an HMI setting like this, if you actually go and click a red pump, it turns green and the physical pump turns on. So, and this can be in a touchscreen setting, or this can be operated from a regular Windows computer. More about that in a little while. This was some kind of heating-related process. I mean, I'm not a process engineer, so I'm not 100% sure even, but there's some kind of furnace that's heating up water. Water flows in pipes. Pretty common ICS stuff. And here's a hydroelectric power plant. And another HMI example. We can see from the top left corner, there's apparently some kind of water pipe or canal or whatever you call these, flowing into this turbine in the middle of the screen. And with this HMI, we can control stuff such as how open the head gates that flow or allow the flow of water into the turbine, how open they are, for instance. And in the lower side of the screen, if you have a look at those few boxes closely, you can see there's input, the rotor blade angle, like you can control the angle of the rotor blade, and you can even set some like thresholds. What's the maximum allowed rotor blade, angle for it? So you can literally, by clicking a device like this, you can control the turbine, you can control the process. And these HMIs in an ICS facility, sometimes they're found in small form factors like this, embedded literally next to those, whether it's like, let's say, next to a conveyor belt that might be controlled with an HMI like this, or you can have them being used in a SCADA system from like an ICS facility control room, for instance. Sometimes the control rooms have more like high-level views, dozens, maybe even 20, 30 screens, different kind of HMIs, whereas in the factory floor, you have one HMI, which is usually used to control the process, which is like a meter away from that HMI. So both of these cases are present. And last HMI-related example, I chose this one in particular because there's a small interesting detail about this particular HMI. And the detail I'm talking about is that there's actually the HMI program is not running in full screen, any kind of kiosk mode like they usually do, but we can actually see that there's a start menu on the bottom. Like, hold on, wait a minute, okay? And it's actually a Windows CE start menu. Looks like this. Some people who were playing around with IT in the 90s or whatnot might recognize this. Not from the freshest edition of the now discontinued Windows CE. And a quick funny story, I actually discovered a device such as this at work a few weeks ago at NCSC. We got a call from a citizen, concerned citizen, let's put it this way. The person informed us that, hey, there is some kind of a heating system accessible online that maybe like shouldn't be. You should maybe figure out who owns this and do something about it. It took us a couple of hours to figure out who was the company operating it, and I still remember my colleague calling the CEO of the company. It was like Friday afternoon or something, and it was pretty funny. Like, hey, I'm calling from the government, and they're like, what? Like, do you have a heating system? Like, I'm looking at this. You're probably not gonna enjoy if I stop this heating system right now. And they're like, no, what's going on? Like, should this be connected to the internet? They're like, absolutely not. Like, oh my God, we need to go fix this right now. And in that particular case, they fixed it immediately, so no harm done there. But it was running this exact same version of Windows, this 90s flavor of the CE. So pretty much whatever Windows exploit you've ever worked with is going to work on a machine such as this. So you absolutely should not expose these online to the internet. Okay, now we have some basic understanding of some of the most important ICS components. What does an attack against ICS look like then? How would an adversary approach attacking an industrial control system? Well, there's a concept called ICS kill chain, which is built on the sort of regular, traditional Lockheed Martin's cyber kill chain that most of you have probably heard of before. Once again, it's not a perfect representation of reality. It's a tool, and I personally think it's a rather useful model that allows us to understand a structure of a cyber operation or a cyber attack a little bit better. Well, both from the offensive but also from defensive perspective. So it gives us an idea at what stage of the kill chain or the campaign the threat actor maybe is when you've detected them, for instance. So like how much time do us as defenders have until the adversary is likely going to reach their objectives on the target. So I mean, that's, I think, all it does. It doesn't model all the cyber operations or like malicious attacks perfectly, but it's a nice concept. And in 2015, a gentleman called Michael J. Asante and Robert M. Lee authored the ICS version of the cyber kill chain, and they published it under SANS institution. This paper is available online. You can go read it if this topic is of interest to you. And the core idea with the ICS version of the cyber kill chain is that it's a two-phase process, basically. So the stage one of ICS kill chain consists of pretty much the same steps what we had in the original cyber kill chain. So we have reconnaissance, we have targeting, exploitation, command and control, and you know, some kind of act or actions on objectives. But now, what the gentleman authoring this paper had found out during their numerous ICS investigations were that there's a distinct separate phase to a lot of ICS-specific attacks that draws a clear line between so-called stage 1 ICS intrusions and stage 2 ICS intrusions. Now, the stage 2 in the ICS kill chain is specifically for developing ICS-specific and that process-specific impact and capability. And we'll come back to this in a little while with a few examples, but the core idea here is that because, unfortunately, all of these facilities that I've personally visited while working for NCSC, for instance, they've had custom systems that are not like one another. So even if you visit facilities operated or owned by one company, you go through like, I don't know, 3 or 4 like power plants or whatnot, not 2 of those are going to be even remotely identical to one another. Which is, of course, horrible from an investigator's perspective because you never know what you're going to run into when you go assist in doing incident response. But it's the same for the threat actors and the adversaries. They're not going to be able to develop generic exploits to cause operational level impact on these systems. So that's why campaigns where this is actually done are usually distinctly categorized into stage 2 intrusions. A few case examples. Let's talk about HAVEX first. So HAVEX was, I guess nowadays we can call it an old school malware already. So it was first discovered in 2013 by F-Secure and Symantec. It's a remote access Trojan, basically, written in PHP. Warms my heart as an old PHP developer that people used to write malware in PHP. And it was reportedly used for targeting aviation, energy, pharmaceutical, petrochemical industries within the US and Europe. The HAVEX infections, how they usually went on about, I think F-Secure Labs reported 88 cases that they were aware of back in like 2013 or 2014 when they published a blog post or an article about the topic. And in majority of those cases, the initial foothold into these environments was gained using exploit kits, phishing and watering hole attacks, after which, due to, surprise, surprise, poor network level segmentation, the threat actors were rather easily able to pivot from IT environments into the ICS environments. And HAVEX is interesting because it's not the first ICS-capable malware. We've had crazy things happening already before HAVEX. Most of you have maybe heard about a case called Stuxnet, for instance. That happened a few years earlier, but HAVEX was still one of the maybe first 3 or 4 ICS-capable malware. And why it's interesting is because it included a network discovery module that was enumerating ICS environments, specifically using an OT protocol called OPC. So we can say that HAVEX was definitely, it was an ICS attack, and it wasn't generic bulk IT level malware, but at the same time, because it only did enumeration, it did not cause any specific impact on the process that the industrial control system was managing. It was purely a stage 1 malware and a stage 1 attack campaign, and apparently intentionally so. Whereas another case example, Frosty Goop from last year, which was discovered targeting Ukrainian energy companies in the middle of the winter. Frosty Goop is written in Go, compiled for Windows, and there are a little bit mixed signals about the initial access in Frosty Goop cases. Majority of the sources report that it was via exploited routers. I think they were MikroTik routers, if I'm not mistaken, some 0-day. People don't patch their routers, and APT gets into them, basic stuff. But some sources also cite that maybe they had this thing that I just explained, us discovering few weeks ago, so somebody misconfigures a firewall and all the components are available online all of a sudden. So I can't say for sure which one was, but all the sources that I found were also talking about the routers. So let's assume that the routers are maybe the initial access. And Frosty Goop was specifically targeting Enco PLCs, so a specific brand of PLCs that were commonly, maybe probably still even today, are commonly used for heating system control. And Frosty Goop is interesting because it's, well, not one of the first, but apparently the first malware that was using a very common OT protocol called Modbus TCP, and not just for enumeration, which is rather common nowadays, but it actually was sending bogus data into the Modbus TCP channels and achieved real stage 2 real-world impact, where what happened was that it caused a 2-day heating outage in Ukraine, where over 600 apartment buildings in the middle of the winter in sub-zero temperatures lost their central heating systems. So thankfully, only for 2 days, they were pretty quick in recovering, but if you compare Frosty Goop and HAVEX to one another, you can see that those are, even though those were both ICS attack campaigns, they had very, very different outcomes and real-world impacts. So that's why I think it makes sense to more or less divide them into 2 categories of ICS attacks. Now this diagram is also from the same ICS kill chain paper. I borrowed it because I love how it illustrates the difference between different kinds of objectives or impacts that an ICS attack might have. And it also, I think, very well illustrates that it's not even nearly as difficult to compromise the security of an ICS environment as it is to really cause specific particular impact on the process that the control system is managing or supervising. Not to mention if you want to do it undetected and you want to do it repeatedly over time, like what happened in the Iran Natanz, for example, the Stuxnet case, it's a whole different ball game than just exploiting some ICS HMI that's accessible online, for instance. So that's something to certainly to be aware of. And I'm not saying when you, as an incident responder, when you go into an engagement, you're not supposed to be thinking about probabilities, really. Like, I just want to be clear on that. Like, you're not supposed to be going in like, it's very unlikely that this is a severe attack. Like, you can't know that. Obviously, you only collect facts and make reasonable deductions based on the facts. But nevertheless, it's important to understand this difference. Let's talk about ICS security briefly. Okay, so we have some idea about the attack campaigns. Now, in ICS security, the most important component of security in ICS is always safety. So traditionally in IT security, we're talking about the CIA triad: confidentiality, integrity, availability. But when we have the cyber-physical domain happening, the actual physical safety of that process is and should always be the first and foremost priority. And specifically because of the cyber-physical component. Obviously, we can't under or like downplay the impact of a whole company being ransomware or hospital losing access to all of their IT systems, where you could have severe things happening due to an attack like that. But in ICS we have this cyber-physical component. What it means is that, or why is it different and significantly different, I would argue, is because if you have an uncontrolled failure in a power generator, for instance, or a blast furnace, which by the way is an absolutely ridiculous device. A blast furnace, which is commonly used in manufacturing, like metal, steel manufacturing. It's an oven-like device where they're essentially maintaining what they call a controlled explosion. There's like molten metal flying around in that oven. If you have, and the temperatures are ridiculous as well. So if a device such as that fails uncontrollably, you're going to be in for a lot of bad time. It's not going to be nice. And it not only causes risk to the environment around, but an immediate danger to you as an investigator if you're next to it, and also the facility staff who are operating that system. So that's a completely new domain for a forensic investigator if you're only used to working with like IT systems. And thus the primary goal of your investigation should always be to make that system safe, first and foremost. So root cause analysis, of course, nice, it's important, but you need to make sure that those things don't explode at your face or at anyone else's face either. And I have a pretty interesting example. Not sure if you all are already familiar with this, but DHS and Idaho National Labs, they did a demonstration in the States in 2007, where the idea of the demonstration was that they took this 27-ton diesel generator, like a big-ass generator, not gonna lie, pretty big, producing over 2 megawatts of power. And they had a protective relay sitting between the test electric grid. They have like crazy equipment down at the Idaho Labs. Like their practice equipment is basically what we run in production, kind of a setup. So they had this crazy big electric grid there, and the generator was hooked onto that, and in the middle there was a protective relay. And the only thing they did was a hacker reversed the logic of the protective relay with 127 lines of code. And the goal of the protective relay is to make sure that there's no physical damage happening to the generator if something happens in the grid or in the generator. But if you reverse the logic, now instead of it being a protective relay, it turns into a destructive relay. And after doing that, what they did was they very quickly disconnected the generator. They ramped it up first, so they started producing power, and then they disconnected it violently from the grid, which is not something that you should do. And so, of course, the generator goes up because all the load is gone, but it's still going full blast. And then they disconnect, reconnect, disconnect, reconnect a couple of times. And the relay doesn't do its job. So the whole 27-ton generator literally jumped in air, started busting out smoke, parts were flying around. So within less than a minute, we go from a situation like this into a situation like this. And this is the last frame before it actually goes so black that it didn't make any sense to have a photo of it. You can find this video online, go check it out if you're interested. But this is a terrifying experiment. 127 lines of code, and essentially this whole generator was rendered completely useless. And if you were sitting next to it, or even within 50 or 20 meters from it, in the same factory floor, that little yellow helmet that you're going to wear in those facilities is not going to protect you if the generator starts spitting out metal and parts and freaking jumping around. A 27-ton generator, like what? That is crazy. So this obviously is a whole new domain into security that we have when we are dealing with these cyber-physical components. Let's talk about the investigation process a little bit. I think it's important to mention that if you already have success with some kind of a process, whether it's the SANS process or if it's the NIST process, or maybe you have your own custom process for DFIR, I don't think it makes sense to reinvent the wheel and have a separate process for investigating industrial facilities. So just stick to the process that works for you. And okay, you're going to have to make probably some small adjustments, like the helmet I mentioned, for instance. Maybe don't go near to the machine if it might explode, these kind of things. But the general idea is going to be the same. So even though the environment might be slightly different, whatever, use the process that already works and is battle tested for you. Well, what are the differences then? Okay, IT investigation, industrial control system investigation. In IT, the network protocols that we work with, of course, it's not a comprehensive list, but it's the pretty basic stuff, has been like it for, I don't know, 20, 30 years at least. It's always the same stuff that you commonly see in an investigation, whether it's cloud, it's on-prem, Windows, Linux, Mac, whatever. So pretty standard stuff. The amount of legacy is usually, I would say, reasonable within IT. It's not nice that there is legacy, but everything is not legacy. So usually it's maybe 20% or 40% or whatnot. And backing up your IT systems is a rather common practice nowadays. Not everybody is still doing it. That's not good, but majority are. And that's going to help you a lot in disaster recovery. Network traffic, okay, is becoming more and more encrypted all the time. But nevertheless, what's helpful is that, let's take like enterprise Active Directory environments from DFIR perspective. Majority of them represent, they're very similar to one another. If you're investigated, like let's say 5 or 10 or 15, you know pretty much what's going to happen. So they're more or less like one another architecturally. The operating systems, binary formats, the script languages that you're used to, hopefully, or maybe even trained to investigate basic stuff. Plus, I would argue there's a reasonable amount of tooling available for IT investigations. And not only tooling, but training offerings as well. So there are a few different course providers, even a lot of free material online that's going to help you get good at regular IT DFIR. Where in turn, if we look at ICS, there's a ridiculous amount of network protocols. Like it's not even funny. I think I've seen maybe at least 20 or 30 different ICS or OT protocols during, like, let's say the last 15 investigations we've done. So that is crazy. Not to mention that, well, I'm not saying many vendors, but a notable amount of vendors have their own. Some are open protocols, some are proprietary protocols, which is just puzzling to me. That everything is like stuff starts to become vendor dependent that much. It's also crazy that brand new facilities are really deployed with already like devices and software that are way past their best before date. Like devices, the Windows 90's CE flavor HMI that I showed you, you can order it online and install it to your new facility even today. I think that is interesting. And I've seen, I think it was last year, there was one obviously not going to mention any names, but one new facility opened, and I think it was Windows Server 2008 that was running the Active Directory, the OT/AD, within that facility. And I was like, it's 2024, like, you sure this is a good idea? Like, hasn't been updated in 10 or 15 years or whatnot. You don't see that kind of stuff happening in IT, thank God. In ICS, often there's no backups available for numerous reasons. That doesn't help with disaster recovery. Okay, some good news. The network traffic in industrial setting is rarely encrypted. Once again, due to many reasons. The equipment can't handle it. Key management is difficult. But that gives us at least some headway in our investigations and threat hunting activities, because we can analyze that traffic when it's in plain text. So that's nice. And now what I already briefly touched upon earlier, each of these ICS environments are unique. So there's usually more or less unique combination of vendors that are involved in designing it. Each vendor handles their own part, and they want to make the best custom solution at the time available with the budget and for that specific process in that specific location. And it just means that each HMI that you see is going to be different. Each combination of PLCs and networks is going to be different. So if you compare it to the AD stuff I mentioned earlier, that is a pain in the butt as well. And no, don't get me started on the like the devices, CPU architectures, ladder logic programming. Oh my God, that is nasty stuff. And the vendor or industry specific things. So let's say you go to distributed control systems in oil refining industry, for instance. Those devices, vendors, protocols are completely different than what you see in, like, let's say, a coffee factory or transportation and logistics facilities or general gas and energy. They're largely different. And I think that is pretty crazy. But plus, there's no such thing as ICS or OT specific investigation tooling. Like, there isn't. So you're going to have to try to adapt your IT tooling into OT or ICS. Plus, what's interesting is that you're going to have to learn to use the traditional automation engineering tooling to do investigative tasks with. So you're slowly turning into an automation engineer the more you investigate these environments. I think that's pretty funny. There are some similarities as well, of course. So thankfully, the workstation operating systems and the server operating systems are largely familiar to you if you've done regular IT investigations. So they're usually Windows-based systems. So that's nice. You can use your regular like evidence collection tools. You can build a super timeline with Plaso, take a disk image, take a memory dump, do the basic stuff. That's really nice. Though you're going to have to remember that, like I mentioned, there's a lot of legacy involved. And in numerous cases, I've personally been in a situation where I can't install Sysmon on the system, it's too old. I can't run no EDR, no tools, nothing will work on it. I need to write like custom PowerShell 2 scripts, or like my colleague would say, do a Rust binary for it. That works. I wonder who that is. But another good thing is that remote management, whether it's legitimate or let's say the legitimate way of remotely managing these facilities, is usually what the adversaries are trying to abuse as well. And those protocols and those mechanisms are exactly the same in IT and in OT. So thank God they didn't reinvent new OT way of remotely managing these facilities. So if you're accustomed to investigating VPN devices and breaches where the initial vector has been VPN plus RDP, for instance, that's going to be pretty much the same stuff you see in these ICS breaches. So that's good news, for sure. So from these early on graphs, these systems that I've marked in here, so these are going to be Windows systems. And these are going to be the systems that the adversaries are very likely going to want to breach if they want information from the facility or if they want to impact the process. So if you are not too late and they're not all cleaned up, there should be some traces that you can investigate with your regular DFIR knowledge and expertise. And same in here. The engineering stations are usually the most important part because that's where the PLC logic is being developed and updated from. So as an adversary, you would most certainly, if you want to backdoor a PLC and stay undetected, you would most certainly do it from the same place where the engineers update the logic of the PLCs. And if it's a Windows machine, then voila, you can investigate it. So I'll leave you with two slides. Some good news and some bad news. And we're going to start with the good news first. Not many threat actors have ICS-specific capability. And that's a fact. So to a lot of them, when they see an HMI like that, when their foothold lands, they're going to be as puzzled as you will be when you, as an investigator, see them for the first time. And not to mention that in order to cause a specific impact to the process, they would need to understand not only the equipment, but also the process. Because let's think about a case, if you attack an HMI, you get access to it, and you launch a ransomware on it. So you encrypted the HMI. The PLC doesn't give a damn. It's going to continue running. It's probably been running in that factory for 30 years. They're just going to switch out a new HMI and keep on going. So that ransoming of that HMI had literally no impact on the operational process of that facility. So not really something that, as a threat actor, if their goal is to, for example, extort money, well, you're not going to have a lot of leverage if your impact was close to zero. Then, well, like I mentioned, the PLCs are programmed from Windows machines, and also, if an adversary is preparing for a stage 2 intrusion, they need to know the process throughout, like thoroughly. They need to know all the versions, all the logic, all the parameters, all the physics of the operational process, and they're going to get it from systems that are Windows-based. So there should be traces, you can investigate them. Same with SCADA systems, should be investigatable. And now here's where we go back to the Purdue model again, why I early on showed that horrible drawing to you. Most of the relevant information for a forensic investigation or an incident response investigation in ICS setting relies elsewhere but the bottom levels of the Purdue model. So it's going to be HMIs, it's going to be engineering workstations, your SCADA systems. Those are going to be the places where most of that activity takes place. And those are going to be systems that we can, without tons of ICS-specific knowledge, we should be able to investigate. And obviously the network traffic part is also good. Like we've been doing network-based threat hunting at NCSC for a little while now. Works pretty well in ICS because you can see everything is in plain text. It's not obviously as good as going to investigate or hunt on the endpoints, but it's an interesting option that you nowadays don't have in IT investigations because everything is encrypted. So in OT, and there are pretty nice tools available, open source and free tools that help you work with this. So that's pretty good. But on the other hand, a simple Nmap scan can literally sometimes bring down whole factories. And you might be wondering to yourself, like, well, how is that possible? If you have a 15 million euro factory built, how can a single Nmap scan bring it down? Well, let me tell you this, some of those components, even if it's a new factory, those components might have been used in production systems for, I don't know, 20, 30 years. Their network stack is not what you find in your regular modern laptop. They were maybe developed by some summer intern 35 years ago, and the PLC's logic is only works and supports you to have, like, let's say 5 open file handles ever open at a time. And if you open a 6th one, everything goes black. And now when you come with the 2025 version of Nmap, you run a scan in the production network, it goes down. So what happens if and when an adversary accidentally causes a disruption that causes a loss of a human life? That is a pretty scary thought. So accidental stage 2 intrusion. I'm not aware of such having happened yet, but I must say that it's probably going to be just a matter of time that something along these lines is going to happen. And I don't think it really matters did that happen intentionally or not, but there's going to be a lot of tough discussions after that case. And I must admit, analyzing automation logic is crazily time consuming. And if you're like a DFIR or IT background people like I am, and majority of the people at NCSC, you're not going to be able to understand the logic of like hydroelectric power plant, for instance. I have absolutely no idea how is that turbine supposed to run and what's the blade angle supposed to be. So I can't make any distinction. Are those changes malicious or are they just normal if I'm observing them over the local network, for instance? Analyzing firmware is crazy, takes a lot of time. I don't like it at all. Thankfully, you don't really need to do it that often. And I would advertise, if you run into ICS cases, well, of any sorts within Finland, give us a call. We're happy to help you. Even if it is analyzing firmware, we'll do our best. I'm not making any promises, but if you have to go down that deep, that's not going to be nice. There aren't too many good quality trainings available, and a lot of these systems shouldn't be online. but they end up being online anyways. So yeah, that's not good news. But I'm going to leave you with these thoughts. Sorry for stopping and ending on the bad news. Hopefully, you also remember some of the good news as well. That's it. Thank you.